Okay, in this video we're going to pick up on Notes 2, page 12, which contains a lot of information that you pretty much need to memorize right away. So let's get down to that. So the first thing is that, I've mentioned this actually a lot if you've been watching all these videos. A Taylor polynomial that's centered at x equals 0 is actually called a Maclaurin polynomial. And that's something you just have to know because the problem will tell you to write a Maclaurin polynomial, and that's by default telling you to center it at 0. So make sure you know that. But also you'll see problems that say Taylor polynomial and center it at 0. So not really a big deal. But it turns out that there are 4 of them that you need to have totally memorized. So here they are. The functions are e to the x, sine of x, cosine of x, and 1 over 1 minus x. So the first 3 are really easy to remember the names of, or, e, sine, and cosine. The last one we call geometric series. So let's take a look at some of the things about them. So these are all Maclaurin polynomials, so they're all centered at 0. First thing to notice, well, I mean, maybe you didn't start off looking at sine, but sine is an odd function. You'll notice that there are only odd powers of x in its Maclaurin, or Taylor polynomial. Similarly, cosine is an even function, and we're only seeing even powers. So that's good because it makes it a little easier to memorize these sorts of things, which you definitely need to do. The next thing you maybe notice is that both sine and cosine are alternating, so they have a -1 to the n. They both start out positive, and then they alternate negative, positive, and so on and so forth. And you just have powers over factorials. So it's, you'll see an x cubed over 3 factorial, and x to the 7th over 7 factorial, and so on. So that's sine and cosine. Here, 1 over 1 minus x is actually a geometric series, so maybe you studied those in like Algebra 2. We know a lot of stuff about them if we did study them in Algebra 2. One thing that I kind of left out here that's really important is that the absolute value of x needs to be less than 1 for this to make any sense. If it's bigger than 1, then you can still plug in. It just doesn't really give you a valid approximation. And later we'll talk more about that. It's called an interval of convergence. For all the other series, they're actually true for all values of x. And then finally we have e to the x, which just actually has all the powers. So it's 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on and so forth. And you might remember Euler's formula, which relates e to the x, sine, and cosine. If you kind of play around with the series a little bit, you'll be able to derive that. I'm not going to do it in the video, but it's kind of a neat thing to be able to do. What I want to do now is show you that you can actually create, by knowing these, you can create an infinite number of new series without actually creating a table of values and plugging in and all that stuff. So let's take a look at that. So the first one, we've got f of x is e to the x over 2. And what we want to do is we want to write a Taylor polynomial. We want 4 non-zero terms and then the nth term. So what we do is we start off, I'm going to take, I memorize the series for e to the x. I'm going to write it, but I'm going to use u instead of x. So I have e to the u is approximately, and then 1 plus u squared over 2 factorial plus u cubed over 3 factorial. So it has all the powers. And then finally I get u to the n over n factorial. Okay, the reason I write it with u is because now I'm directly going to substitute. So everywhere I see a u, I'm going to replace it with x over 2. So I get 1 plus, and now I'm going to replace this u with x over 2. And then I'm just going to keep going. Every u gets replaced with x over 2. So I actually typically write this out. It's kind of a waste of time. I mean, you'll see as I go through the video that I start skipping steps because it's a little easier to skip the steps because it's just a lot of writing. And this I would not leave like this. Usually I don't like to leave anything in parentheses to a power, so I will rewrite it. 1 plus x over 2, and then I'm going to have x squared over 2 squared times 2 factorial, and then x cubed, 2 cubed, 3 factorial, finally x to the n over 2 to the n, n factorial. And there you go. Let's take a look at another one. I'm probably going to do B, C, D, and E in this video, and then come back in another video to do whatever, the remaining ones. Okay, so let's say we have cosine of 3x, and you'll see I do every one of these problems basically the same. I'm going to write cosine of u. So cosine, it's an even function, so I just get even powers. It alternates, so squared over 2 factorial, 4 over 4 factorial, 6 over 6 factorial. Then I got negative 1 to the n to make it alternate, u to the 2n over the quantity 2n factorial. Make sure you put 2n in parentheses there because of the way factorials work. Now I'm just going to replace every u that I see with a 3x. So this is the process. I call this building a series. I don't really know if it has a true name. I mean, I guess substitution. But I think it's helpful if you start off with a series written in terms of u, and then you just make your direct substitutions. So this, and then after I'm done with that, what I like to do is kind of expand everything. So what I'm going to do is actually just jump to the expanded. So there you have that. You pause it if you want to compare. Just raise everything to its own power. Let's take a look at C. Okay. So the function for C is x over 1 minus 4x. And what I'm going to do is I'm going to rewrite this and kind of color code some things. So I don't actually know what to do with x over 1 over 4x, but 1 over 1 minus 4x. But what I do know is some way that I could kind of deal with 1 over 1 minus u. So I'm going to rewrite it. So I'm going to pull out the x and then make it 1 over 1 minus 4x, which I've written in a different color just to kind of get going. So now what I'm going to do is focus on 1 over 1 minus 4x. That looks a lot like my geometric series, which I know to be 1 plus u squared plus u cubed. I find the geometric series to be the weirdest one, the way it just works out. Just powers of u. That's strange. And now substitution. So we just directly plug in, and we have all these 4x's in here. And so the next thing I'm going to do is I want to take, well, let me expand that. So this is all expanded out. Now what I'm going to do is multiply both sides by x. So times x, and then got to do it to this side also. And so on the left-hand side, I get the series that I was looking for. And on the right-hand side, or rather the function I was looking for, on the right-hand side, I'm just kind of increasing the power of x by 1 to all terms, because that's essentially what happens when you multiply through by x. So I have this, and there you go. So not so bad. So let's do one more. So this one, our function is x squared sine of 2x. And you can see I've kind of color-coded things again, just to make it a little clearer what's going to happen. So we're going to start working on sine, and then at the end we'll just multiply through by x squared. So we know that sine of u, sine is an odd function, so I'm going to get all the odd powers, which is really how I remember it. Sine and cosine, they alternate. Sine is odd, so odd powers. Cosine is even, so even powers. So we get 2n plus 1. Again, parentheses around the 2n plus 1, and then factorial. So now I'm going to go through and plug in 2x everywhere I see a u, and I'm actually going to kind of skip. There we go. So that's what you get when you replace every u that you see with a 2x. And I like to, again, break everything apart, so I don't like to leave something in parentheses to a power. So I have this, and now I'm going to multiply through by x squared. So on the left-hand side, I get the function that I was supposed to write a series for. And here, let's multiply by x squared. So that's going to make everything have 2 more in its exponent for x. So I end up with 5th over 3 factorial, and then 7th over 5 factorial, 9th over 7 factorial. And then when we get to the general term, we do basically the same thing. I'm just going to add 2 to the exponent of only x. So instead of having 2n plus 1, I have 2n plus 3. And there you go. Okay, so I'm going to come back in another video and do problems E and F for no particular reason other than this video is kind of dragging on. So I hope you found this helpful, and good luck.